Okay, so let us continue. So example 9, 5.3, self-inductance. Apply self-inductance L equals to negative EMF over di over dt for coil and also for solenoid. Now in your syllabus, it's going to focus more on this equation. Okay, so L equals to negative EMF over di per dt. So questions 1, example 9. A 500 turn solenoid, this is your N, is X cm long. So you have L right here. When the current in the solenoid is increased from 0 to 0. From 0 to 2.5 ampere in 0.35 seconds. Now, current is increased from 0 to 2.5. So this is your I initial, this is your I final. Okay, in a time 0.35 seconds. The induced EMF, this is your EMF induced, is 0.012 volt. Given mu naught is 4 pi times 10 to the power of -7, calculate the inductance of the solenoid. So how to calculate the inductance of the solenoid? Well, we have equations L equals to negative EMF di over dt. If you expand these equations, it is equals to negative EMF I final minus I initial over dt, right? So which is then equals to negative, negative EMF here is 0.012 over, I final is 2.5 minus 0 over 0.35 second. So the answer is equals to, L is then equals to 1.68 times 10 to the power of -3 Henry. Okay, -3 Henry. So that is the answer for questions A. So start from this equation. So you have to know how to use these equations, especially when you're given I, the current, the change in the current. So from 0 to 2.5, that means that is a change. Change is a di, I final minus I initial. The cross-sectional area of the solenoid. So you have a solenoid. You want to calculate the area. So L is equals to mu naught N square A over L. Over L. So you want the area. Now, area is coming from which equation? It's coming from these equations. The equations that we use to determine what is the things, what is the factors that will affect the values of inductance. So from questions A, we obtain inductance 1.68 times 10 to the power of -3 is equals to mu naught given 4 pi times 10 to the power of -7. Numbers of turns given is 500. And then A given, do we have A? No, that is the things that we want to calculate. And then the line is XCM, which is 0.08. Rearrange the equations. The cross-sectional area is equals to 4.28 times 10 to the power of -4 meters squared. So that is the answer for questions B. Questions B. Now, question C. You have to be careful. Question C is asking for final magnetic flux linkage. It's asking for flux linkage. So it's asking for capital letter phi, not the small letter phi. So how are we going to calculate? Well, if you recall, the equations that we have is N phi equals to Li. This is the equations that we have. So if you're looking at flux linkage, remember, this whole thing is known as flux linkage. This whole thing is known as flux linkage. So it is equals to Li. So which is then equals to L given is a 1.68. 1.68 times 10 to the power of -3. Currents given is final, okay, final, so it's 2.5. So it is equals to 4.2 times 10 to the power of -3 Weber. So that is the answer. All right, so you have L, you have A, and then you have the flux linkage. So flux linkage, now these questions, these are last questions, you have to be extra careful, okay? Because this is where students always got it wrong. Because you forgot about linkage, the term linkage itself. Linkage means more than one turns. Okay, so it's N5, the whole thing. Biasanya pelajar memang salah di sini. Okay, pelajar biasa kira flux equals to Li over N. This is wrong. This is for magnetic flux. Okay, this is for magnetic flux. Okay. This is for magnetic flux. Kalau soalan minta Anda kira magnetic flux, then you use this one. But if question is asking for flux linkage, then remember, this is the equation. Okay, so this is linkage. All right, so I give it 2 minutes to write it down before we proceed to the next question. Okay, so let's look at example 10. Yeah. Okay. Example 10. A solenoid of length, again, you are given an object solenoid, and then length given 25 cm with an air core. Air core means there's nothing inside solenoid. Consists of 100 turns, so this is capital letter N, and a diameter 2.7 cm. Calculate the self-inductance of the solenoid. Now, when it comes to this question, try to ask yourself, which equations can be used to calculate self-inductance? Let us begin with the definition. Okay, so questions A. If we use L equals to a negative EMF di per dt, do we have enough information? Apparently no. What we have is just a fixed current, 1.6. We don't know what is the initial, what is the final value. Okay, we are just given the value at one moment. So, well, this is not the equation that we're going to use. The second equation that involve a self-inductance is a N phi equals to Li. Now, do we have enough information in this case? Once again, if you look at these equations, apparently no, because we don't have the flux. Okay, we don't have the flux. What we do have is just I and the N. We don't have a flux. Meaning that we're going to proceed to the next equations, where we're going to use L equals to mu naught N square A over L. So this is the equations that we're going to use. All right, now In exam, if I'm not mistaken, kalaulah tak silap saya, I think this equation is not given. Okay, I think this equation is not given. So if it is not given, then what are you going to do? You have to calculate, you have to start it by using B equals to mu naught N, I over L. From here, you obtain B, then you proceed to phi equals to BA cos theta. Okay, once you have this one, then you apply N phi equals to Li. Okay, to calculate L. So L equals to N phi over I. So this is what you can do. If you cannot memorize, you cannot remember this equation. Okay, if I'm not mistaken, this is not given. But then you can calculate by using this step. Step 1, step 2, step 3. It's going to be a long step if you can't remember these equations. Okay, now that you have these equations, okay, so you plug in the value. So remember to calculate A. Okay, A can be calculated by using D, which is A equals to pi D squared over 4. Okay, which is then equals to 5.73 times 10 to the power of negative 4 meters squared. So once you have it, plug everything into the equations. Eventually, you should obtain L equals to 2.88 times 10 to the power of negative 5 Henry. Okay, negative 5 Henry. So that is questions A. Okay, that is questions A. Now let's look at questions B. The energy store. So energy store, you have just one equation. Straight away, you can apply the equations. U equals to 1 over 2 L I squared. Just one equations. All right, so plug in the value and you should obtain 3.69 times 10 to the power of negative 5 joule. Okay, 3.69 times 10 to the power of negative 5 joule. So that is the answer for example 10. So once again, I give you 2 minutes to write it down. All right, and I encourage you to write down the solution in the green color. Okay, I want you to learn. If you cannot remember these equations, then what are you going to do? This is the alternative method. Okay, alternative method. So 2 minutes for you to write it down. Okay, so now let us proceed to example 11. So example 11, A current of 3 ampere flows in coil C and is produced a magnetic flux of 0.75 Weber. When a coil D is moved near to coil C coaxially, a flux of 0.25 Weber is produced in coil D. So like I told you just now, the flux across C and the flux in the D, they are not going to be the same because it experienced a flux leakage. So if coil C have 1,000 turns and a coil D have a 5,000 turn, so what happens right here? Oops. Okay, no, never mind, can use it. So we have this one, okay, this one with a current. Okay, this one with current. And then this one is without current. Okay, this one is without current. So this is a coil C. And this is a coil D. Coil C and coil D. So what happens right here? Coil C, it comes with a current IC equals to 3 ampere. Now, when it comes to two coils, that is how I like to do it. I draw a diagram and then I put the information about them below the coil so that you can see which information belongs to your primary coil and which one belongs to your secondary coil. So a flux across C is 0.75 Weber. And then NC is equals to 1,000 turns. Coil D, okay, coil D, it doesn't come with a current, so no I, but it do have a flux D, which is equals to 0.25 Weber. And then ND is equals to 5,000 turns. Okay, 5,000 turns. Calculate the self-inductance of coil C and the energy stored in C before D is moved near to it. So you want the self-inductance across C. Now, if you look at the information that you have right now, you have I, flux, and N, meaning that you can actually apply the equations. N flux equals to Li, but of course, they are all coming from C. And C, flux C, L for C, and I is also coming from C. That's why we call self-inductance. Everything is coming from itself. So plug in the value 1,000, 0.75, okay, and then equals to LC, I given 3. Rearrange equations. L is equals to 250 Henry. Okay, 250 Henry. Then when it comes to energy, so energy in coil C is equals to 1/2 LCIC squared. All right, plug in the value, you should obtain 1125 joule. Okay, 1125 joule. Next question, it asks you to calculate mutual inductance. Mutual inductance, now the tricks on how to solve it, you look at the current. Current is coming from C, meaning that all the other information must be coming from D. So the equations that we're going to use right here is ND flux D equals to mutual inductance, but I is coming from C. You look at the I. If I is in the first coil, then all the other information you use it from the neighboring coil. If I is in coil D, then you use flux and N from coil C. Okay, so you look at the I. This is IC. The rest is D, but this one is C. So plug in the value. Okay, plug in the value. N is 5,000. Flux is 0.25 equals to M, and then I is 3. Rearrange the equations. M is then equals to 417 Henry. Okay, 417 Henry. So that is how you solve it. So question C. If the current in C decreasing, now your current is decreasing, means that it has a DI here. Okay, from 3 to 0 in 0.25 seconds. So this is your I initial, this is your I final, and this is your T. Calculate the induced EMF in coil D. So how to calculate induced EMF in coil D? Okay, so remember, induced EMF is equals to negative M. The current DI should be coming from C. So DI over DT. Okay, so remember, induced EMF D, you use it because it's mutual inductance. You use the current from the neighboring coil, right? So it is then equals to negative M I final minus I initial over dt. Now, when it comes to this di, I encourage you guys to write it down. Okay, to write it, to expand the equations into I final minus I initial. If you are given the value in terms of a statement from 0 to 3, from 3 to 0. Why? Because it doesn't mean 3 here. Okay, from 3 to 0, it doesn't mean that di is equal to 3. From 3 to 0, because your final is a 0, therefore, di is equal to negative 3. If you are not expanding the equation, most of the time students, they tend to forget that from 3 to 0 is a negative value. Students will tend to substitute the value as 3. Okay, kalau kamu tak expand, kalau kamu tak tulis keluar I final tolak I initial, apa yang terjadi dalam exam biasanya pelajar terus anggap di sama dengan 3. In fact, it is wrong. Why? Because your final is smaller than initial. So it should be a negative value, right? So your your EMFD, it is then equals to negative 417 I final 0 minus 3 over 0.25, which is then equals to 5004 volt. Okay, 5004 volt. So that is your question C. Okay, that is your question C. So A, B, C. Remember, A is self-inductance. Okay, self-inductance, which occurring in coil C. Okay, and then these two questions is mutual inductance. Okay, the questions related to mutual inductance. So now I've got 3 questions right here. I give you 3 minutes to write it down before I proceed to the next question. All right, now let us look at the next one. Okay, next questions. Example 12. Okay. Example 12, two coils X and Y. Once again, you have an X and Y, two coils are magnetically coupled. The EMF induced in coil Y is 2.5 volt. When the current flowing through coil X changes at a rate, so a current changes at a rate, meaning that this value given right here is actually di over dt. Okay, di over dt. So what you have is the EMF induced. So this is your induced EMF in coil Y. So calculate the mutual inductance of the coil. Now this one, the current flowing in X. So this one, okay, I'm going to rewrite. Oops, I'm going to rewrite it. It should be dIx over dt. So EMF Y. So the mutual inductance of the coil, EMF Y equals to negative M dIx over dt, because you are looking at mutual inductance. Therefore, EMF Y, the current must be coming from X. Okay, the current must be coming from X. Okay, now this question is where you have to be careful. When you have diy divided by dt, okay, if your diy, if your di is a positive value, then what does it mean? It means your EMF would be negative. Why? Okay, why? Remember, if your I increase, B increase. If B increase, then your flux will increase. Flux increase give you negative EMF. This is the tricky part of this question. So even though you are given a positive value right here, but because of this set of relationship, therefore this one, it should be negative 2.5. Okay, so equals to negative M dIx over dt. Plug in the value. Okay, I'm just going to plug in, which is 5. So rearrange the equation. M is then equals to 0.50H. Okay, so means that if you have an I decrease, okay, means that you are going to get di is a negative value. Okay, if your di is negative, then your EMF induced would be positive. Why? Because if I decrease, B decrease. B decrease, flux decrease. Flux decrease, it will then give you positive EMF. All right. So this question, the tricky part is EMF. It didn't tell you whether it is positive or negative, but it tells you your I is now positive. Okay, your DI is positive. DI positive, which you should know that I increase. What does it mean by I increase? It means B increase. What does it mean by B increase? It means flux increase. What does it mean by flux increase? It means you have a negative induced EMF. Okay, so the crucial part, the crucial thing in this question is these two relationship. You have to understand, you have to know, you have to memorize. Okay, you have to memorize. Okay, next questions. If EMF induced in coil X, the EMF induced in coil X, if there's a current flow, now they change the question. Initially, you have current in X. Okay, so initially, this is what happened. So this is a current. Okay, and then this is a galvanometer. This is your X, this is your Y. In the second questions right now, it tells you, you change the situation. Now your X is the one with galvanometer and your Y is the one with current. Okay, so the induced EMF in coil X, if there's a current flowing through coil Y, which change at the rate 1.5 A and then S -1. So how are we going to calculate it? We're going to calculate it by using the same equations. Just that now, because we have the current in coil Y, so this one is now diY over dt. So EMF X equals to negative M diY over dt. Now, what happens to the M? M is still going to have the same value. Why? Because now you are not changing the numbers of coil. You are not changing the cross-sectional area. You are not changing the length of the solenoid. Okay, everything they are being kept at the same thing. The only thing is you change the positions of galvanometer and the battery. Therefore, M is still equals to 0.50 Henry. Okay, because you are not changing the physical structure of these two pieces of solenoid. So they're still going to have the same mutual inductance. So EMF X is then equals to negative 0.50. Okay, the rate is 1.5. Therefore, EMF X is equals to 0.75 volt. Okay, so the crucial part in the second question, in the questions B, is you need to know M is equals to 0.50. Why? Because you are not changing the physical structure of both coils. Okay, the only things that you change is just the positions of galvanometer and also the power supply. The rest, they remain the same. Therefore, mutual inductance is remain at the same. Okay, so example 12, I'll give you a few minutes to write it down. Okay, I want you to write down the relationship on the right-hand side. This is particularly important in chapter 5. Okay, chapter 5, kenapa pelajar tak boleh score? Biasanya pelajar akan salah di sini. Okay, because you guys don't know one is a positive, one is a negative. When to use flux, when to use flux linkage, and so on. Right. So a few minutes for you to write it down before we proceed to the last questions in chapter 5. Okay, So now let's look at the last questions. Example 13. Example 13, once again, you have two coils, coil X and Y, they are magnetically coupled. Coil Y has a 50 turns, so you have this one, color, this one. And Y 50 turns, and then a current of 2.5 ampere flowing through coil X. So this is IX. Produce a magnetic field so that the magnetic flux of 35 amp Weber passes through coil Y. So this is your flux Y. Okay. So questions A. Determines the mutual inductance of the coil. Now, obviously, we know already how to use the equations because we have IX. If you have IX, then the ways the equations are working to you is Ny flux Y equals to IXM, okay, or MIX. MIX. Okay, so you're using the current from coil X, therefore the other information must be coming from Y because this is mutual inductance. So plug in the value, I have a 50 right here, 35 milli equals to M, 2.5, rearrange equations, mutual inductance is equal to 0.70 Henry. Questions B. The current of 2.5 ampere changes to 4.5 ampere. I initial 2.5, I final 4.5. In time 2 times 10 to the power of negative 3 seconds. Estimate the average EMF induced in coil Y. Okay, so this information is for coil X, and then for coil Y, okay, now you want to calculate the induced EMF. So EMF Y is equals to negative M dIX over dt. Once again, because you are looking at mutual induction process. So which is negative 0.7 and then final, I final minus I initial over time. Okay, which is then equals to, okay, you plug in the value and you should obtain 700 volt. Okay, 700 volt. So now you have all this information, plug it in, and then you try to press a calculator, you should obtain 700. All right, that is how you solve example 13. Okay, example 13.